Chapter 2, Part A, Graphing Quadratics. In this lesson, we'll look at different forms of quadratic functions and the shape of their graphs. Lesson 2.1 is titled Vertex Form. We'll start off by looking at transformations, something we talked about in Topic 1. A quadratic function, again, this is just review, is any function of the form f of x equals x squared or any type of transformation of that. This is a non-linear function, and the parent function has a vertex at 0, 0. From lesson 2.1, it says describe the transformations to the parent function f of x equals x squared. Then graph the function. This would be our parent function. If we made a table, we had a table like this back in topic 1. We know the vertex is 0, 0. If I plug in 1, I would square it and get 1, and the same thing would happen with negative 1. If you plug in 2 and square it, you'd get 4. Same thing with negative 2. Let's plot these 4 points to see what the shape of our graph would look like. There's the basic shape for our quadratic function, parent function. Now let's look at the transformation. H of x equals 2 times x minus 1 squared minus 3. If we describe this transformation in words, we would say that that 2 stretches vertically. So all those y values will get a lot bigger, a lot faster, twice as fast. The x minus 1 would mean it moves 1 to the left, and the minus 3 after would mean the whole shape would move down 3. So if you remember in our tables from topic 1, we take our original points and we create a new table. Left 1 means all of our x values, we're going to subtract 1. So I'm going to take everything in this column and simply subtract 1 from it. 0 minus 1, 1 minus 1, negative 1 minus 1, 2 minus 1, and negative 2 minus 1. Then take a look at the vertical stretch by 2 and down 3. That means we'll take all of our outputs and multiply them by 2. And then down 3 means we subtract 3 from them. That's what we're going to do to all of these numbers. Let's start with 0. 2 times 0 is 0 minus 3. 1 times 2 is 2 minus 3. Again, 1 times 2 is 2 minus 3. 4 times 2 is 8, minus 3 is 5, and then we would get 5 again. That's how we got our new ordered pairs for our transformation. Let's plot these points and see if our shape on the graph does what we described it as doing. If we look at the shape of our graph, it looks like it stretches vertically. It's more narrow than the parent function. It moved to the left and it moved down. So it did all the things we said it was going to do. But that seems like a lot of work every time you're asked to graph a quadratic function that has a transformation. There's got to be a better way, and we'll talk about what that looks like when we talk about vertex form. First things first, a parabola over on that left-hand side. A parabola is just the name of the shape that's formed. So it's the name of the U shape. The graph of a quadratic function is a parabola. Let's write that down. The graph of a quadratic function is a parabola. Uh-oh. I have a message. I better shut my phone off. All right, let's take a look at what it means to be in vertex form. The equation of a quadratic function in vertex form really is just looking at those transformations. Y equals a times x minus h squared plus k. So it's still quadratic because we have that squared, and the a, the h, and the k are numbers that will be in the equation. Instead of having to describe the transformation every time, we're going to look at what's called key features for a quadratic function in vertex form. That way, we won't have to describe it, but when we're done with our graph, it would look like all the parts we'd think it would normally look like. Looks like there are a lot of steps, but really there are only 3. When you have a quadratic function in vertex form, you want to find the vertex, the axis of symmetry, and where it crosses the y-axis, the y-intercept. If you know you're in vertex form, the vertex of your quadratic function follows the h and the k. So whatever h is on the inside is going to go in the opposite direction. Whatever k is on the outside, it goes up or down. So we've done that before, but now we just don't have to describe it. The next thing we do is we actually draw in that dotted vertical line, that axis of symmetry. And the axis of symmetry is an equation. You have to have x equals h as the equation for that axis of symmetry. Last but not least, we look for the y-intercept. To get the y-intercept of the graph, we have to plug in x equals 0 and then simplify. And then we plot that point. Here's what it looks like on the right-hand side. It says, state the key features for the quadratic function f of x equals 2 times x minus 3 squared plus 4. Then graph. We should be able to do this without having to make the big table. Thinking about our key features, the first thing that we'll determine is the vertex. Thinking about the h and the k value, if it's x minus 3 in the equation, the x-coordinate will be positive 3 for that vertex. It moves 3 to the right. The number that's being added after is 4, and that means the vertex would move up 4. And that's all you do, 3, 4. And that should seem pretty familiar to us. We talked about the vertex with all of our transformations. The second thing we're going to do is find the axis of symmetry. And you really don't have to do any work. The axis of symmetry is always the same number as the x-coordinate of the vertex. We're going to write it as an equation, x equals 3. The third thing we need is that y-intercept, and this takes a little bit of work. We have to plug in 0 for x in the equation, so I'll start it off as y equals 2 times 0 minus 3 squared plus 4. And now we simplify. That should be an equal sign right there. There we go. 0 minus 3 is negative 3, and negative 3 squared is 9. 2 times 9 is 18, plus 4. Oh boy. That's too far off of our graph. That's crazy. All right, so let's take a look at what we can do. If we plot our vertex, 3, 4, 3 up 4, I'll draw in my axis of symmetry in orange right here, just that dotted vertical line. Our y-intercept is pretty big. That's kind of far off of our graph. So if that's too far off of our graph, we will have to make a quick table. Oh, and I said we wouldn't. Sorry about that. All right, so that's too far away. We know for sure that 3, 4 is on our graph. So let's go ahead and pick another point close to 3 on the x-axis, like 2, and simplify. 2 minus 3 would be negative 1, and negative 1 squared is 1. 1 times 2 is 2, and if I add 4, we get 6. That's a point we can plot on the graph. Over 2, up 6. And now reflect that point to the other side. Let's see if we can get one more point to fit on here. Let's plug in 1. 1 minus 3 is negative 2, but negative 2 squared is 4. 4 times 2 is 8, and 8 plus 4 is 12. Ugh, that already goes off of our graph, way up here. And then I'll maybe throw that on the other side just for good measure, like so. Go ahead and draw a curve through those 5 points. And without having to make that big table up above, we've sketched the graph for our quadratic function in vertex form. And now it's time for a little throwback. State the domain and the range for f of x, and we will use interval notation. The domain for this function, if we go from left to right, even though those arrows point up, the graph is getting bigger for that parabola. So the left side and the right side, it's going up, but it's also opening on the left and right, which means for our domain, the x values would go from negative infinity to infinity. They would keep going. You can pick as many positive and negative numbers as you want. The range, think bottom to top, that's where our vertex comes into play. The bottom of the vertex, or the y value, is the smallest number for our range. And since those arrows both point up, it goes to positive infinity. And that's enough for today. Please make sure you have all these notes written in your packet.